systems are almost invariably lagging in power factor. Having one or more leading loads, that is the overexcited synchronous motors on the system, can be used for the following reasons. First one, a leading load can supply some reactive power Q for nearby lagging loads instead of it coming from the generator, since the reactive power does not have to travel over the long and fairly high resistance transmission line. The line current is reduced and the power system losses are much lower. As it is depicted by this previous example, we have seen that the reactive power demand of the induction motor was partially met locally because of the overexcited synchronous motor. So this resulted in a reduction in the current in the transmission line, which result in reduction in the transmission line loss. Part 2. Since the transmission lines have to carry smaller amount of current, they can be smaller for a given rated power flow. It means we can use smaller diameter transmission line conductors, which will result in lower cost of the transmission line and ultimately lower cost or reduced cost of the power system. Part 3. In addition, requiring a synchronous motor to operate with a leading power factor means that the motor must be operated in overexcited condition. This mode of operation increases the motor maximum torque. How? We are familiar with this relation. If sine of delta is 1, that is delta is equal to 90, then the maximum torque will be 3 times V phase EA sine of delta by omega m xs. We can see that the speed is constant because the synchronous motor speed is proportional to frequency, and it cannot change. A synchronous motor is an exactly constant speed motor as compared to the different DC motors and induction motors we have already discussed. Since the speed of a synchronous motor is proportional to frequency, as the system frequency is constant, so the speed of synchronous motor is exactly constant. Xs is constant for a motor. Similarly, V phase is constant for a motor. It means that the maximum torque is proportional to EA. If we increase the field current IF, it will increase EA. So it will increase the maximum torque. In other words, we can say that larger the excitation, more will be the maximum torque of the motor. The use of synchronous motors or other equipment to increase the overall power factor of a power system is called power factor correction. Since a synchronous motor can provide power factor correction and lower power system costs, many loads that can accept a constant speed motor are driven by synchronous motors. Although these motors are costly as compared to induction motors, however, their ability to operate at leading power factors for power factor correction saves money for industrial plants. The reason is that the industrial consumers have to pay for their reactive power demand as well. They have to pay for Q. A domestic consumer pays only for the real power demand, kilowatt hours or real power P. However, the industrial users have to pay the real have to pay for the real power demand as well as for the reactive power demand. So if they manage to improve their power factor, their reactive power demand will decrease. So the electricity bill they have to pay will also decrease. However, running a synchronous motor in overexcited condition requires a high field current and flux, which can cause heating of the rotor. An operator must be careful not to overheat the field windings by exceeding the rated field current. Synchronous capacitor or synchronous condenser. A synchronous motor which is purchased to drive a load can be operated in overexcited condition to supply reactive power for the system. In fact, in the past, sometimes the synchronous motors were purchased and run without a load simply for power factor correction. Such a motor phasor diagram has been shown in figure 5.14. You can see that in this case, this is V phase. Here, The motor is operated in overexcited conditions, so EA is larger than V phase, and you can see that this is the current IA is leading the voltage V phase by exactly 90 degrees. So rotating this phasor in counterclockwise direction, we can have JXS IA. The difference of basically the motor is operating in overexcited condition. So EA minus JXS IA is equal to V phase. You can see that the real power supplied by this motor is zero, as it is operating as a purely capacitive load. So this motor is not supplying any real load, it is not supplying any mechanical load. Since there is no power being drawn from the motor, the distances EA sine of delta and IA cos of theta are zero. You can see that here E sine of delta component is EA sine of delta component is zero. Similarly, IA cos of theta component is zero. So the real power supplied by this motor is zero. It is only used for the power factor improvement, and is acting like a capacitor on the system. This motor at no load is just acting like a capacitor on the system. So in the past, there were some motors that were sold only for the power factor correction purposes, and these machines had shafts that did not even come through the frame of the motor. It means that the shaft of those motors were not available for putting some mechanical load on the system, and these special purpose synchronous motors that were used for just power factor improvement are known as synchronous capacitors or synchronous condensers. Condenser is an old name for the capacitor. V curve for a synchronous capacitor is shown in figure 5.15a. You can see here, as we are increasing the excitation, the armature current is decreasing. Initially, the motor is operating at lagging power factor. It is consuming reactive power. At some point, the armature current will become almost zero. It will be just equal to the losses supplied by the motor. The armature current drawn by the motor will be only that is required to supply the losses taking place in the motor. As the motor is supplying zero load, so the armature current is approximately zero, just sufficient enough to supply the losses. If we further increase the armature current, if we further increase the field current, the armature current will again start increasing. In other words, the motor is now supplying reactive power to the system. It is operating in leading power factor condition, and the same has been depicted by the phasor diagram for this motor. V phase is constant. IA1, the initial armature current, and the initial excitation is IA1, so the drop is JXS IA1. If we increase the excitation, the voltage EA will increase, EA2. The difference between V phase and EA has increased. It is now JXS IA2. Since XS is constant, it means that armature current has increased. And for further increase in excitation, we can have a third figure which corresponds to EA3, JXS IA3 and IA3. Since the motor is supplying no real load, the shaft of the motor is not available for putting some mechanical load. So it means that the motor is used only in this condition for supplying reactive power to the system, and its current is leading the voltage, the supply voltage by 90 degrees. It is the case for this region. The phasor diagram has been plotted for this region where the armature current is leading the supply voltage.